All right. Good afternoon, everybody. I'm very pleased to welcome Dr. Guy Brasseur here for our distinguished climate lecture. Dr. Brasseur started at the Free University of Brussels, where he got 2 engineering degrees and a PhD, and then went to work for the Belgian Institute for Space Aeronomy, where he worked on middle atmospheric chemistry and transport. In 1988, Dr. Brasseur moved to NCAR, and in 1990, he became the director of the atmospheric chemistry division there. In 2000, he moved to Hamburg, Germany, and became the director of the Max Planck Institute for Meteorology. He served as the chair of the Scientific Committee of the International Geosphere-Biosphere Program and as lead author for the IPCC Fourth Assessment Report, for which he and the rest of the team received the Nobel Prize. In 2009, he became the director of the Climate Service Center in Hamburg, and he's now an external member of Max Planck, as well as a distinguished scholar at NCAR. He's also chair of the Joint Science Committee of the World Climate Research Program. I had the pleasure of getting to know Dr. Brasseur during atmospheric composition and the Asian monsoon meeting. We had dinner one evening as part of the meeting, and I sat next to Dr. Brasseur. And I can tell you that despite all of his accomplishments, he is one of the kindest and most open-hearted people you will ever meet. And I'm very pleased to welcome him here to JPL today.
Thanks very much, Jessica. I'm really pleased to be here at JPL. It's been a long time since I visited the area and the laboratory, and you're doing such great works that we like to refer to a lot of things, a lot of products that are coming out of your research. So I'm really, really happy to be here. And so today what I would like to do, and I know that a number of you and colleagues are listening to us from other places in the world, what I'd like to do is really to talk a little bit about the evolution of atmospheric chemistry from what was a very, and still is, a very intense research activity into a more operational activity where the realization that the information we gather could be useful to society is really becoming prominent. And so let me indicate that the background, the reason for making this presentation is because internationally we're working very hard at the development of an international network through a project called MapAQ, which is sponsored by the International Global Atmospheric Chemistry Program, IGAC, and by the World Meteorological Organization. And the idea here is to develop prototype and build strategic coalition in the world towards the development of a network focusing on global air pollution, the monitoring of it, the analysis, the prediction, and the attribution, and that at different scales. Now, perhaps if I talk about air quality and atmospheric chemistry, I should start with the point that things have changed dramatically. The Industrial Revolution that started more than a century ago was really the pride of many countries, showing how the activity was enhancing the capability of the country. And that was the case in the US, this was the case in China, everywhere. People were proud of having a strong industrial activity. And of course, the consequence of that has been a growing concern on the impact of these activities on the environment and the occurrence of a strong smog episode. So impacts of air pollution has become obvious. Health effect, and you know what they mean. Loss of crop yields and problem perhaps with food security, reduction in visibility, problem of the deposition on the biosphere, and acid precipitation was very much in the news, and many other aspects, including climate forcing. The cost of air pollution was also calculated, and in the OECD country plus China and India, very polluted, the cost was estimated to be about 3.5 trillion. And if you look at what happens, for example, in the European region, the costs were extremely high, also assumed to be higher than about 1% of the GDP in most of these countries, and that in spite of the efforts made to reduce air pollution. Now, not longer than a week ago, July 8, 2022, the New York Times published a paper, an essay, an opinion paper by David Wallace Wells, who is a climate journalist very interested in the evolution of climate. He realized that air pollution is a serious problem and that air pollution kills 10 million people a year, roughly. Why do we accept that as normal? Why do we care so little about the consequences of air pollution? So how can we address the problem? Certainly through a number of short-term action, and that's by avoiding air pollution episodes, and in particular, the need of air quality forecasts to see what kind of action needs to be taken can be very useful. And so we'll talk a bit about, in fact, quite a bit about air pollution forecast. On the longer type side, mitigation is, of course, very important, and that requires that we identify the sources of air pollutant and to take then the appropriate action to reduce them. And of course, adaptation is another aspect where we need to change people routine, and this has led a number of groups to go to very high resolution individual forecasts for you on your phone of what you should do and not do. So let's start with a historical perspective. And when we talk about air pollution, in particular ozone episodes like the one that existed in Los Angeles very much, we have to go back to Pasadena. And in the early 50s, Hagen Schmidt, who was a Dutch scientist who moved to the US, made the hypothesis that, in fact, the production of those ozone episodes came really from the release by cars, by automobiles, by industry of hydrocarbon and nitrogen oxide, both coming together, reacting in an atmosphere that was submitted to very high solar radiation. But 20 years later, in the early 70s, another very important piece of information came out, and Hiram Levy II noted that a small fraction of oxygen atoms, metastable oxygen atoms, produced by the photolysis of ozone can react with water vapor and produce the hydroxyl radical, the OH radical. And that has led to the understanding that the atmosphere is an oxidizing medium and that OH reacts with almost all chemical constituents in the atmosphere, producing at the end a number of secondary pollutants, ozone being probably the most important of it. And this is the scheme that in 1971 Levy showed to explain tropospheric ozone. Of course, we know now that this is more complicated. There were a number of studies made by Crutzen and Chamides who showed that ozone in the troposphere was not the result of intrusion of ozone from the stratosphere, as it was believed until the 70s, but was really the result of photochemical reaction. And the ozone chemistry appeared to be basically the connection of VOCs and NOx, in the presence of solar radiation, to produce ozone in a city like Los Angeles. We know now that it's a bit more complicated, that there are a lot of reactions involving oxidants like OH and HO2 that are playing an important role. And in fact, we even know that the schemes that are involved can be very different depending on the chemical environment in which you are, so that you need really to see what happens in any region of the world where the situation can be very different. Now, moving to more recent time, the US Academy of Science started or published a report called The Future of Atmospheric Chemistry Research, and indicated, I'm quoting them, our understanding of atmospheric chemistry has advanced sufficiently that it is now clear that the field is central to addressing vital, important societal issues. And addressing this issue depends on a deep understanding, of course, of atmospheric chemistry as the basis for the development of reliable predictive capability across local, regional, and global scale. So there is a recognition that we need to go beyond the investigation of fundamental processes, but see how this knowledge can help society to respond to a number of problems, in particular air pollution. Well, in Europe, the same idea came up, which led to the formation of a European program called Copernicus. Copernicus is one of the flagship programs of the European Union. There's several Copernicus services, one on climate change, which is essentially a climate service, one on marine monitoring, one on land monitoring, one on security emergency management, and there is one on atmospheric services, which basically try to provide information about air quality anywhere in the world, with focus, of course, on the European regions. So I mentioned that there are long-term response, but there are also short-term actions that are needed. And I would like to go through them a little bit, highlighting the importance of observations, but also the analysis of these observations, and then the predictive aspect, the forecasting, that help us also understand how the system is functioning. Now, forecasting air quality is not a trivial issue, because if you want to do it in particular on the global or the regional scale, you need to rely on a number of important input. First of all, you need a good meteorological forecast. Not only the dynamics, but also the water cycle, the precipitation, and so on. You need to get surface emissions. You need to get observation to validate your model, or maybe to assimilate data in your forecast. And then you need to do a prediction. You need to evaluate, to validate it, and constantly to improve your product. And that requires, of course, the presence of both space or in situ observation. So the element of air quality forecasts are shown here: in situ monitoring, remote sensing observation, global and regional modeling, anthropogenic and natural emissions. So let's go to some of these aspects, and let's start with the emissions. Emission inventory is a tricky business, because the people who are working very hard on these aspects get very little support from the agencies, because it doesn't appear to be a real scientific problem. It's more like an inventory, establishing an inventory. And in fact, it's a very, very important aspect. So here's an example of an estimate of the global emissions of carbon monoxide. And of course, you see that the emission is mostly important over the continent, in industrial region, maybe in regions where biomass burning is important. You even see the signature of the ships who are releasing carbon monoxide over the ocean. But then if you look at different inventories and different attempts to calculate those values, and you pick a country like here, China, you see how diverse the inventory are and how uncertain, therefore, the emissions are. I'm going to show you here, for example, 3 inventory of carbon monoxide over China. The one at the top are essentially based on the Chinese establishment of the inventory through the MAKE project. The one in black is what ECMWF is using for the CAMS project. And you see that they are very different. And in particular, they're very different regarding the trends that we see. And when we want to look and understand trends, for example, of ozone, we rely on those emission inventory, which are very different. So there's still a lot of uncertainty. Another aspect that's important in the emission is the spatial resolution. Today, the global inventory, or most of the regional inventory are established at about 10-kilometer resolution. But models now treat atmospheric chemistry perhaps at 1-kilometer resolution or even better. And so there is a need to downscale those emissions that we get from the inventory based on proxy that we can be taking, like here, for example, if you take ammonia emission from agriculture, you get the 10-kilometer resolution, then you get a proxy, which is the cropland fraction, and you can use that to try to improve your emission and come to a 1-kilometer resolution. You see it here also for the emission of carbon monoxide associated with transportation or residential aspect. This is all in the vicinity of Beijing. This is a work that my PhD students have been doing at the moment, but it's very useful because you can see that when you put that in a model, you see the influence of these downscaling, and you see it's relatively important. So let's go to the second box of the forecast, which is remote sensing observations. And here we have seen tremendous progress. Of course, I cannot resist to show you a TROP-OMI NO2 distribution, which I think is a kind of a very nice way of showing activities around the world. With the high pollution in Asia and still in Europe, the biomass burning effect, etc. Europe, under this Copernicus project that I'm referring to, has a number of plans to launch a number of Sentinel spacecraft that you probably know. But it is important also for the people who do air quality forecast. This is here the number of basically satellite products that are assimilated into the Copernicus global prediction system for air quality over time. And you see that the numbers has been growing, the satellite involved has been growing, and of course the quality of the prediction has been also improved. We are now waiting, of course, for the new generation space observation, which will be based, or at least one of the new generation type of satellite, which will be the geostationary satellite. GEMS has been already launched by Korea. We're waiting for TEMPO at the end of this year, and then the Sentinel-4 that Europe will be launching. And of course, our community involved in modeling and prediction needs to adapt to that, because the assimilation of this type of data is a bit different than what we have been doing up to now. But at least we will have a very dynamic vision of how pollution is evolving. Let's move now to the modeling aspect. And of course, here we should indicate that we need to look at different time scale, but also spatial scales, starting from the global scale, going all the way to continental, regional, local, and urban scales. We can even go increasingly to smaller scale, such as the urban scale I mentioned, but also taking into account, for example, the interaction with buildings at a very high resolution scale. Now I'm getting stuck. Okay, so let's go a bit through those different scales and show some example of predictions that are made. I referred already many times to the Copernicus Atmospheric Monitoring Service, which essentially provides global maps of prediction on the global scale at a resolution of 40 kilometers and twice a day, so every 12 hours. You can see the number of observations that are processed every 12 hours and the number of maps that are released every day. And of course, these data are just complemented by different utilization of these prediction to help in different issues, air quality, ozone layer, climate forcing, radiation, etc. So you can see the type of products that come out of this daily forecast. You get, of course, global analysis. By the way, Copernicus did also 20 years reanalysis of the past composition of the atmosphere, and that can be very, very useful. But then there is a downscale aspect to provide higher resolution air quality forecast. And I'm going to pass this. This is the forecast for CO for today. So, yeah. And so at the global scale, so we can look what happens more specifically over the US. And you see quite a lot of amount of CO on the East Coast, but also on the West Coast. You see here a zoom towards California, where we are. And then, of course, we would like to downscale this further and see how we can provide higher resolution information. So what CAMS is doing over Europe, they have instituted a multi-model ensemble that includes 9 different models, operational models. They are listed here. And I'm going to show you an example here. You see, for example, I think it's ozone on the left, NO2, and CO, PM10, PM2.5, and SO2. You see what the different models are providing at a certain date, and you see also the mean and the median value. And in reality, if you go closer, you will see that the median value is generally better when you do the verification. In general, it's very difficult to beat the median value. So sometimes one model might be better than the median value, but in general, statistically, the median value provide better prediction than individual prediction. I'm going to show you an example of this kind of downscaling, but this time for China. And this is a joint project between European groups, they are listed here, and Chinese group. And essentially what we have been doing for 5 years on a quasi-operational basis is to take, essentially 9 forecasts. We call it N, but it's 9. They are post-process. They are sent every day to a central database. We do a forecast for 3 days. We calculate the ensemble, we generate images, and so on. And this is here, for example, what we did in my lab, where we get essentially the meteorological forecast from NCEP. We get the boundary conditions from CAMS from the global model. And we take some emissions. We do some spin-up every day. And finally, we do a 3-day forecast in China. And we provide that to KNMI. And this will be then disseminated to other groups. This is an example here of a forecast. You see the forecast in red. I'm sorry, in black. And every hour, we obtain a value of the observation, which is essentially an average made by, well, it's an average of several stations which are measuring, let's say, NO2 and ozone in this case. And every hour, then we add a point and we compare the forecast with the observation. If you want to know exactly how we do it, I can go in detail a bit later on, but I won't do it now. This is another example here of ozone and PM2.5, NO2 and ozone over 3 days. And you see that sometimes the prediction is really acceptable, but sometimes it is not. And for us as scientists, it's very crucial to understand essentially why the prediction is failing. And we learn from that, and we can do a bit of science to understand exactly what was happening. This is another example here. I'm not going to show that into detail, but it is an example here for Sao Paulo, where we're using different models, and we do some correction on the emissions to improve the prediction as the time progresses. Let's say a word about local downscaling, and in particular, people are more and more interested to know what happens where they walk, in their streets, in their neighborhood. And of course, the problem becomes much more complicated because the interaction with the surface is very, very complicated. We are now in an urban boundary layer. We have buildings. We have the dynamics is very difficult to calculate, and we cannot afford to do the calculation in great detail. So, for example, in Hong Kong, we have been using, Hong Kong is interesting because the topography, because there is an ocean, and because you have Street Canyon. And so we have been trying to use essentially large eddy simulation to basically downscale what the regional model is providing. The top three panel shows NO, NO2, and ozone from the mesoscale model, so no LES, for the Hong Kong, part of Hong Kong. The resolution is about 1 kilometer, in fact 900 meters. And then we embed into the mesoscale model, which is the WRF-Chem model, an LES that includes the chemistry, includes also emissions at higher resolution, taking into account traffics and roads and other type of information, ship tracks and so on. And then we get to distribution that are very different and much more information. And that's not only true for the surface value, but also for the vertical distribution. You see now that the dynamics is much more complicated. It's, of course, somewhat chaotic, but it shows the vertical motions in the boundary layer associated to convective activity. And if we compare with the measurement at some station in the city, we see that very often the use of the LES improve the comparison with the measurements that are made. But of course, that needs to be further analyzed. Of course, we can also include now buildings, and some people in the group in Hong Kong are also trying to do that with a very, very high resolution model, but I'm not going to talk about it. This is here just to show you another example, which now becomes more and more operational. This is an initiative taken in Delhi by a group that is part of MapAQ, the network that I was talking about, where they try now to do a full-blown daily prediction at a resolution that goes down to 400 meters and is then compared and validated. And it is part of a process to support decisions. So it is really done not just to do the prediction, but to communicate it to authorities who might be taking action. In particular, what this project is doing is to do a source apportionment of the of PM2.5 in this case, and really show the basically the source, where the sources of these different compounds is coming, and that helps then authorities to perhaps take action to suppress some of these emissions. And so they have a public dissemination system that shows you not only the prediction, but also the sources of the pollutant that are predicted to occur. Finally, I'd like to say, as we talk about a prediction model, that the idea is not to look very much in a separate way how global, regional, and local processes occur, but try to combine the different scales into a mesoscale model. So at NCAR, we're now trying with the community to build the Musica system or model, which is a multi-scale infrastructure for chemistry and aerosol, and using essentially grids that allow a zooming capability in certain regions. So one of the model is based on spectral element. That's the grid that is used by the climate Earth system model at NCAR, or using the MPAS grid, which is an hexagonal mesh This one has non-hydrostatic capability and allows you to go to much higher resolution. On the left, probably 14 kilometers. On the right, you can go to less than 1 kilometer. And so it'd be ideal to couple essentially global effect and regional effect in a single framework. This is an example here that we did in Hamburg using that model with a grid refinement for South America and we want to develop an Earth, basically an air quality system for the entire continent of South America based on that model and taking into account also influences from remote region. One of the advantages of this kind of multi-scale model is that, contrary to a regional model, is that air that gets out of the domain can be recycled in the domain if circulation if the circulation is such that some of the air is returning into the original domain. Finally, what I would like to do is to say a word about going beyond the research, but communicating or trying to develop a prototype for specific services and do that with the participation of the private sector. In fact, the European Union wants to cross what we call the valley of death. In other words, to make sure that advanced products and services that the scientific community has been developing over time be communicated outside the scientific community, be even exported to other countries and used by potential users. And so we have been trying to do that in a consortium called the AQWatch Consortium with the participation of different European groups, usually scientific groups, but also participation in other countries outside Europe in order to have a number of prime users who would be working with us on the development of the product and finally use that with potential local customers. So we have been developing 7 products and services. One is a global and even a regional atlas of air quality and over the last 20 years, and so that we know how air quality in each point of the world has been changing. More traditionally, the daily forecast of air quality in metropolitan areas, a service on dust and solar energy forecast. Solar energy companies are very interested. A service on wildfire visibility service, a service on information about air pollution from fracking operation in case some people would like to start fracking in their country. An attribution service which focuses in particular on agricultural sources, and then an emission mitigation service. So here are the product. We're going to pass this. But what is interesting is the process. The process is what we call the feedback spiral. So in other words, we start with a number of ideas that we have. We have a dialogue with prime users distributed in different countries of the world. They help us to develop the service or improve the product that we have in mind. It's being reevaluated, and then we go 3 times. And finally, we hope to commercialize these products after a business model has been established. So here are the basically 5 modules under which are the 7 products. Here's just an example that I would like to show you. This is the global atlas, and there is also a regional atlas. And so we're trying to convince a number of public authorities and municipalities to understand that it's important for them to understand air quality in their region and how it changes over time, make informed decisions about improving air quality. And so we have been testing this with several users in different countries, US, Chile, China. And you can see here essentially the model of interactions. You have the 5 modules that we have been putting together. We have identified the potential stakeholders in addition to the public services that are on the other side. And I'm sure that many of you are interested in trying to develop those basically exchanges with the external world outside the scientific community. And so we try to work with a number of small companies. Some are listed here that exist in the world. We are dialoguing with them. It's pretty long, it's pretty complicated, but we hope that something will come out of it and that some of the products will be essentially used. A word about now the long-term challenge. And a long-term challenge is not so much to predict what's going to happen in the next day, but it's really to find what are the sources of the problem, can we attribute the sources, and can we mitigate air quality. And so more and more, in addition to prediction model, we're thinking of developing basically mitigation strategies based on a number of source attribution information. And so one of the modules that is part of this AQWatch project is to develop exactly that, to provide information on the attribution of air pollution to different sectors and countries and simulate the reduction of emission from a polluted source and demonstrate the effect of air pollution in this region. I'm going to show you that a bit in more detail in a second. Here, for example, we have been developing source attribution services for PM, NO2, and SO2. We have been testing that in 2 regions, Chile and Colorado. We did another study for attributing the sources of carbon monoxide, this time in Colorado. And here you see, for example, in the case of PM, NO2, and SO2 in Chile and in the US, and you can see on the graph that is below where, this is for PM10 in this case, where are the sources of the number of microgram per cubic meter that you see. And you see, for example, residential combustion is a big source, but the others are also shown here. And that helps you develop a mitigation strategy. Then this is another example here for the CO attribution in Colorado. And this is based on tagging CO from different sources. And in this case, you can see that the largest source in red is the source of CO that's coming outside Colorado. And of course, this is to be expected. But anthropogenic activities in the region of Denver are the second most important source. So when we have this, we need to provide a tool for decision makers, for the people who are in charge of air pollution. And so this shows you here a very simple system that exists where basically you start to see what is your concentration. In this case, it's PM 2.5. And then you can play with the button, and you can see here we have reduced air traffic to 76%, residential combustion reduced by 75%. And in this case, you can see how much the air pollution is changing. So that's a tool that is very interesting to users because they can play and say, what if we reduce traffic? Would it make have a consequence on the air pollution in this part of our region? So this is the kind of things that we're trying to develop and work then with the private sector to see if they can put that somehow on the market. Let me conclude now by highlighting a number of challenges. And so I've been putting here essentially 5 challenges that I think are important. First of all, we need to continue to support research and even relatively fundamental research to address what are the unresolved problems. And there's still a lot of scientific questions that are on the agenda. I'm giving here just 2 or 3 examples. Organic chemistry is very complex, with a lot of problems that remain to be addressed at a fundamental way. Same thing for aerosol physics and composition, as well as the role of heterogeneous processes in the atmosphere and how they affect the gas phase compound. The second point is that I think we need to develop a consistent international monitoring system of air quality with a particular effort in low-income countries so that they provide information with a coherent quality standard. I mean, we have a lot of gaps, we have a lot of instrument, we have very different quality in what is produced. I think we have to improve the accessibility of satellite data. I mean, you have a lot of data, but are they used? Are they used? Can we add value to these products to make them really usable for customers and for people in society? I think we need to accelerate also the execution of chemical modeling system. Chemical models are very expensive. They cannot be easily included in climate models because they're just too expensive. Can we find, through artificial intelligence, system that would allow us to be more effective in doing predictions? And then I think we need to include all that in Earth system modeling concepts and approaches. And let me just show you an example here. This is a private company called Plume Labs. They're providing air quality forecast on your phone every day. They're all based on neural network architecture. And they're using low-cost sensor information everywhere in the world. It's an interesting approach. This is their prediction, I think for a couple of days ago, everywhere in the world. I don't know how good they are. In fact, they might not even care so much about how good they are. They care that they produce them and that people buy them or something like that. But maybe we can do better. This is now the prediction. I think it was CO, I forgot now, but I think it's CO. They probably took into account a fire in Canada somewhere. I tried to go further because they claim they can go to very, very high scale. This is Los Angeles. And then I said, let's go to Pasadena. And so this is this is ozone. And so this is the kind of things that they are giving. But what is the scientific quality of that? Can we do better? But maybe the technology might be interesting. And finally, I would say that chemical models need to be increasingly embedded into comprehensive Earth system approaches and models in particular, because chemistry cannot be isolated. It's part of Earth system. It's part of what society needs to address. It's related to climate and weather, to human health, to ecosystems. It has a lot of societal impacts. They are shown here. This is taken from the US Academy report. But again, we should see the problem of the future of the Earth on different time scale as one single problem. So thank you very much. I tried to go through what I think is an evolution of air quality research today. And you can realize that there is a lot of work beyond this. And in particular, I'd like to thank a number of people who have been working with me on these different aspects. And thank you for attending and listening to me. Thank you.
Do you have any questions for Guy? Chip. And can you use the mic for people online?
So thanks, that was really enlightening. And I was taken throughout with the parallels that you see between the air quality problems and the greenhouse gas problems. And I wondered if you see a vision where those two could be brought back together rather than being kept as separate problems.
Yeah, it's a bit unfortunate that the connection between the atmospheric chemistry community and the climate community focusing on greenhouse gases is not stronger. But I see a lot of effort in a good direction. I was mentioning, for example, Copernicus, and now Copernicus is starting a project on the carbon cycle. and involves a number of people who are involved also in the atmospheric monitoring aspect, so in other words, in atmospheric chemistry. And so my last slide was really trying to call for a more holistic view that should basically push atmospheric chemistry into not so much another climate community, but a real Earth system community. And that includes also ecology, biogeochemistry. All these aspects are there. And in fact, here at JPL, you're extremely well positioned to take that holistic approach.
Guy, thanks for a compelling presentation as always. I wanted to focus a little bit on the last two parts. You mentioned attribution as being an important long-term challenge, and indeed we know that long-term exposure to pollutants is one of the key epidemiological challenges that we have. But when I looked at the techniques that you're talking about, often those related to, say, source apportionment type approaches, but they're not what I consider full inverse modeling attempts to really take, when I see exceedances over a season, where are the sources? What is the chemical transformations to those sources? And as we go to very high resolutions, like you mentioned in the Musica project, with geostationary sounders providing very high resolution measurements, proper inverse modeling techniques will be facing some substantial computational challenges. So I just want to see if you could elaborate a bit on where you think the role of doing that level of attribution needs to go in the support of this longer term vision, and how that might be reconciled with the growing data satellite record.
Yeah, thank you for raising this question, because just like you, I've always found that these attribution studies are a bit simplistic, the way they approach them, by tagging essentially a number of products coming from different sources and then trying to see what really dominates. It's an efficient way. And we use that, for example, in a project by USAID in Indonesia, in India, because we cannot afford too long runs to, complicated runs to do that. But theoretically, it's an inverse problem, and it should be done by inverse approaches. And so I've been thinking about that, because basically to do that, you need to build an adjoint model, for example. That is difficult to do when you have a complex model. Could we use artificial intelligence to do that? Could we try to establish links between emissions and concentration, and then use that basically lookup table or information based on training your system to really derive, the intensity of a source. And so we are kind of starting thinking in that direction in order to keep something that can be done at a relatively low computer cost.
Randy, can I ask you to wait just 1 minute? We have Stan Sander online was going to ask a question. Thanks.
Hello, Guy. This is Stan Sander. Thank you for a very enlightening talk. I was delighted to see that under future challenges, you highlighted the need to support research, including organic chemistry in the atmosphere. And indeed, there are also many poorly characterized processes in inorganic chemistry that remain. So chemistry is at the heart of all of the modeling efforts that you have highlighted. And yet there seems to be a reluctance on the part of many modeling groups to stay current with the state of the art in our understanding of these processes. We have a number of notable examples recently for fundamental discoveries on organic proxy radicals, reactions of HO2, both low NOx and high NOx systems. I wonder if you've noted the same thing. What accounts for this rather, I would call it sluggish approach to adopting and validating chemistry fundamental elementary processes in the modeling work that you've described?
Well, you know, models, when I started my career, had probably 20 reactions. And they have been getting more and more detail as a function of time. And today, a global model and even a regional model, probably with higher spatial resolution, might have typically 250 species and a certain number of reactions. That's putting the model to the limit of what you can do on a computer in a reasonable amount of time. So when the chemistry community comes up with a new process, what the modelers need to do is, first of all, think about the potential importance of adding a number of chemical schemes that will cost some money in their model. I'll give you an example. At NCAR, we have the Mozart scheme that we've been using. I forgot how many species, how many reactions. And now we have made it much more complicated by adding a number of organic species. The model is 3 times slower, and the ozone or other species that many other species that you calculate are 1 or 2% different. And so you just say, well, is it really worth to do that? So I think what the approach should be, because I agree with you that there is perhaps a tendency to reject something that doesn't appear to be that obvious to the modelers, or maybe they're not convinced. I think the approach is really to work with 0D model that are very, very detailed chemically. And then if a new concept comes in, a new reaction comes in, or a new set of reaction comes in, is really to test it in detail in those chemically resolved models to see under which condition these new processes affect the system. And so I think I can understand a bit that you are desperate or frustrated to see that the modelers are kind of reluctant to do that. I think it's because they might not have detailed 0D model where they can really focus on the chemistry and the chemistry only. And I think every modeling group should have on the shelf a very hyper explicit chemical model and try to see if a new process comes in, what is the impact? And if it has impact, then it has to get in the big model somehow.
Great, thank you.
So Guy, I wanted to follow up a little bit on what I'll term as the accuracy of forecasts. And I noted in your talk that when you were talking about it, I believe it was the CAM service, that you used an ensemble of different models. And then when you talked about the Plume Labs, you mentioned about not quite knowing how accurate it was. Could you comment a little bit on where you see us going and trying to quantify uncertainty and giving the users some sense of the accuracy of forecasts? And how do we approach actually defining that?
So in the case of the regional downscaling, both in Europe and China, which are the two areas where we've been working, we had a number of models. In the case of China, it was 9 models. We made an assumption that they were independent, which is, of course, an important assumption, but sometimes it's not a real assumption because the models, get parts from other models and so on. But let's assume for a minute that each model is independent, and then basically what those 9 models give you is a distribution of results. And so you could ask yourself which model is better than the other. You can also calculate the median. You can calculate the mean. And then you can compare with your observation. And what we saw was that the median, in particular, was usually better than any model. So essentially having a larger number of models than 9 even is very useful, because you really get a distribution, and the distribution gives you a sense of the error you're doing on the prediction. So going in that direction is probably one way to do, and ECMWF or Copernicus go in that direction. They increase the number of regional models to do the downscaling, and they improve that. This is one way. They indicated it's one way to improve their prediction. For what regards the artificial intelligence or deep learning methodology, I don't think we know enough about that now. It's really starting. You know, Daniel Jacob was telling me 2 days ago that they're trying to do this, and they realize that, you know, it is accelerating the process, especially if you do air quality forecasts on a short time, you know, like just 2 or 3 days. But if you want to do chemistry over a century to complement maybe a climate model, you have no guarantee that your system is stable. So you have to be very, very careful. And number 2, the cost is not so much reduced compared to what you would happen with the traditional model. And the errors are pretty large still. So I think it's an open question to see if we can go in that direction, but it's a question that we should address.
Guy, Chip asked the question about the linkage between the carbon system and air quality, and it seems to me that, you know, there's been a disconnect for many years. You and I lived it when we were both at NCAR. But it seems to me that there's an emerging issue that makes it even more important that this artificial stovepiping or cultural disconnect be addressed, and that is that we're now in the post-Paris Agreement world, where major global effort is being put into the mitigation of greenhouse gas emissions, and of course that's going to have a huge impact on the emission of air quality precursors and constituents, and it might actually change the strategy and the emphasis. So, for example, if fossil fuel combustion is simply going down dramatically, which we hope it will, everywhere, perhaps the emphasis on longer-term mitigation needs really to focus on the non-fossil contributors to greenhouse gases. But we'll also need to understand atmospheric chemistry in a future world that isn't dominated by the energy emissions, which are probably the majority, or at least the plurality of air pollutant emitters as well. And this, it seems to me, requires a very deep dialogue between the two communities that honestly I don't actually even see the beginnings of. The emerging dialogue doesn't go to that level of what a carbon and air quality look like in a world with a fundamentally different energy technology mix.
Yeah, and one example, of course, of what we could see in the future in that regard, because climate change will occur, is the number of fires and wildfires that will increase dramatically. And that has an impact on the carbon system, but it also has an impact on air quality. I mean, at the moment, Portugal, France are burning, or at least in large fraction. A year ago or so, it was here in the west of the US, and you have fires in California also at the moment. So it seems that we will have a very different nature of air pollution and carbon systems. And so it might be a good opportunity to, really build a kind of a view of what the world will look like after, let's say, fossil fuel are not used as extensively as they are now. So that could be a good starting point, in fact, for communication between those two communities.
All right, so we need to wrap up. Let me have everyone join me in thanking Guy one more time. And thanks to everyone online who joined as well.
Thank you, Jessica.